All right, so last time I discussed the relative entropy method, and we saw several improvements of it. The work of Jabin and Wang that's able to treat some singular cases. The ideas of Dan Leiker to obtain some improved convergence rates. And I should mention now that there is also there is a possibility to obtain global in time convergence with the relative entropy method. By using functional inequalities. So you remember that when you differentiate the relative entropy, you obtain a negative term, which is the Fisher information or the relative Fisher information here, grad, something like that. And what you can do is you can try to exploit this term, this negative term, by trying to show that this is bounded below by essentially a little constant times the relative entropy itself. And so if you can do that, then you can hope to prove something of this form, right? And so this is going to require some sort of functional analysis, functional inequality that's adapted to this energy. And if you can do that, then with Grandval, of course, you get exponential in time. You now get global in time convergence and exponential in time. And so for, I refer you to recent work of Guillain, Lebris, and Montmarché, who do that in the context of the Jabin-Wang situation. Okay, and so now today I want to finish this cycle of ideas with the question of treating the case of Courant type or Riesz type interactions, but with noise. So what about Courant Riesz with noise? Okay, so there's two approaches now. One is there is work of Rosenzweig and myself, where we adapt just the modulated energy approach. And it works for the sub-Coulomb Riesz cases. Sub-Coulomb Riesz, which is, if you remember, a singularity strictly less than d minus 2. So these are some cases where there are these other approaches that also work. You remember the Jabin setups. But here we use the framework of the work with Hung. Okay. So the same modulated energy that I described for that. And then you compute the expectation, basically the derivative of the expectation of the modulated energy. And you're able to show that you can control it. So the important thing here is that when you differentiate in time, there is a term that involves that is going to involve singularities of the form Laplacian of g x minus y times empirical measures minus rho. And this term essentially has the right sign in this context, s less than d minus 2, right? It's the superharmonic case. So the term appears and has the right sign. So eventually it's negative and you can throw it out and you can show this type of relation, which of course then suffices to conclude in the usual way. Now for s equal to d minus 2 or more, there is the work by Bresch, Jabin, and Wang. And they treat also more general interactions as well, but I'm here focusing more on these inverse power interactions. So the work by Bresch, Jabin, and Wang, what they did is they made this important observation that you could combine the method of Jabin-Wang based on relative entropy and the modulated energy method into a modulated free energy method. So they define a modulated free energy. And the energy is the following. So sorry, it's not an expectation. It's not what I wanted to write. Just an E of Fn relative to rho. So remember, rho is going to be our limiting density, the expected limit density. So you take the relative entropy as before, and you add to it beta over 2 times the average with respect to Fn of the modulated energy. Okay, so here you have relative entropy, and here you have modulated average modulated energy. Okay. So why is this called a modulated free energy? Because we're in statistical physics. The free energy is something of the form beta times energy plus entropy. And typically that's the kind of thing you want to minimize, in fact, in statistical mechanics models. So here there is a 1/2, you see, it's not beta, it's beta over 2. This is because of the normalization of the modulated energy. Because the way I define the modulated energy, each interaction between the I and j, the pair interactions I and j, is counted twice. It's counted for I and then it's counted for j. So that's why you should divide by 1/2 if you want to be exact. And here the precise constant that's in front is very important. So it's important to keep this 1/2. In the previous computations here, it doesn't matter if I multiply f by a constant, so changes nothing. But here it's very important because these two terms have to be combined in exactly this way for the method to work. Okay, and so now the big miracle somehow is that when computing dTE, which is of course dTH plus beta over 2 dt of this other term, some cancellations happen. And these cancellations make exactly the problematic terms disappear. So if you remember when we were differentiating the relative entropy, there were some terms coming out that involved the divergence of the kernel K. And that's where the Jabin-Wang method assumed that divergence K was pretty good. But in the case of Coulomb or super Coulomb Rees, divergence K, well, divergence K, which is like minus Laplacian G, that's pretty bad for Coulomb or Rees with S bigger than D minus 2. But when you differentiate the average relative entropy, modulated energy, what you find coming out is exactly the same terms, and they cancel. And they cancel because you put exactly the right factor in front. So it's not completely a coincidence. It's because this quantity is a good physical quantity, or is the right physical quantity for the system. The cancellation is a little bit tricky to see, but I will try to give you a flavor of it. It's very computational. But so once you have that, okay, you prove this proposition. So, okay, Bresch, Jabin, Wang, they were working in the torus, and they had a framework that, in some sense, was a little bit similar to the framework with Hung and Matt, because they're allowed to relax a little bit from being exactly an inverse power. But okay, you once you see the cancellation, you can apply this on the whole space. There is not really a difference. And the main important proposition is the following one: is when you differentiate. So okay, so assume Fn solves the Liouville equation, you know. So where is the equation written? Okay, so let's write it. Then we put the minus here. Okay, and rho t solve the limiting mean field equation. Dt rho t plus divergence minus divergence grad g involved with rho t equals 1 over beta Laplacian rho. Then dt e okay, so we're gonna have all these terms, minus 1 over n beta, integral of fn sum over I. So this is the negative term, right? Which is a sort of relative Fisher information properly. I don't know how to call it in this context, but like that. So K here is always, so K is minus gradient of G. And then you have the second term, which comes with 1 over n squared. So here you want to recognize grad G x minus y dotted with v of x, which you can symmetrize like this, v of x minus v of y. And here you have this like that. And so what you recognize, you see now with this, essentially the proof is done, because here you have a negative term. And here you have a term for which you can apply the functional inequality that we call commutator estimate, and that you can bound by the average. So here there is an extra averaging. Okay, so do it like that. So do integral of fn times all that. Okay, so it's the average of this quantity that's in the commutator estimate, and v, the particular velocity field that you should take here, is gradient, so it's minus gradient log rho plus beta. Okay, convolved with rho, so that's essentially the velocity field associated with this equation. So this is v depends on time, and this is okay. So I could be off by a factor of 1/2 somewhere, and maybe maybe there's a 1/2 here because I've symmetrized, and by possibly a minus sign. Okay, so with this and the commutator estimate, we obtain dTE less than minus, less than plus C times the integral of Fn times the modulated energy. And that in turn you can bound by CE itself, because the relative entropy has a sign. So when the relative entropy has a sign, and the modulated energy almost has a sign because it's bounded below. Okay, so you can control each of them by E. So this is since F, and H are both bounded below. Okay, so it's really a sort of algebraic simplification that does it, but then all the technical analysis tools are there, can conclude. What's difficult is to recombine the terms to obtain precisely this square and to obtain precisely this form here. Okay, so I will show you maybe the beginning of the computation to give you a flavor. But we are not going to finish it because it's quite long. Okay, so first you have the time derivative of the relative entropy. So that's That's what we've seen before. So there was this negative relative Fisher information terms. So if you may remember, there were terms like this. Okay, terms like that. Okay, so I think these were essentially the terms. And then you have what you have to do is you have to differentiate Fn of f x and t rho t in time. And so that you have to differentiate two things. First, you differentiate Fn, and then you differentiate the rho t part. So that's a bit, okay, that's a bit long. Okay, so you have beta over 2 integral of dt Fn f of x and t rho t, for which you're going to use the equation of Fn plus beta over 2 integral of Fn tt f relative to rho and t. So let's call this one 1, and let's call this one 2. So for 1, you remember you have this equation, dtfn equals all of that. So we have to plug that in. And so when you have the divergence, that's the divergence that's here, is going to hit on the modulated energy Fn, F, right? So the divergence is going to hit F. So that you're going to have some gradient of F that's hit with whatever is in the formula. So I write it like that. Okay, and so now we have to compute what's the gradient of Fn. So you look at Fn. Remember what this was defined to be. And you look at the point where there is dependence in xi. So, okay, so you have all these terms, sum of g of xi minus xj. These are going to come out. And then you have the interaction of where you have g of xi with rho. Okay, so there's going to be two types of terms. And that's going to bring you something like that, grad g xi minus y. So that's the interaction with the other terms. And then you have the interaction with rho, but this one comes with a 2 because of the symmetry of the expression. So you have something like that. Okay, which you have to plug in to plug into 1. And then for 2, you observe again. So you have, this is the expression of f of x and rho, and you have to differentiate it in time when there is a rho t here. So you're going to use the expression for rho t. I mean, the equation that's solved by rho t. Okay, so dt fn rho t. That's going to be minus 2 over n sum over I integral of g xi minus y. And here you input the PDE. Well, this is all of that. Of y. And then you have another term where you differentiate the part that's rho t interacting with rho t. So you see, this is the interaction of rho t and the Dirac, and here there's the interaction of rho t and rho t. Okay, so now when you do some integration by parts and you regroup the terms in a wise way, you obtain something like this. So you remember that k is the gradient of rho. You see, whenever I have Laplacian here, I can put them on rho, on g, sorry, and you're gonna get some gradient g terms, so that's gonna involve them, k xi minus y. Y. Okay, so I'm going to stop with computations at this point because it becomes a little bit tedious. You can, of course, look at the computations in the paper by Bresch and Jabin Wang. They organize it a little differently than what I'm describing, but this is a way to get the result. So of course, so here you can recognize a few things. So for example, here this velocity field is going to appear. So you can recognize here the minus gradient log rho plus k convolved with rho times rho, which is v rho. So this is v times rho. That's, so you see, this is a piece of the term. This is a piece of this term. K x minus y dot v of x times this. And the other thing you can recognize is you can recognize terms that involve diff k. So you see like terms like this, or even terms like that. And that will cancel with the corresponding terms in the derivative of the modulated energy. This one, for instance, you can also recognize as k convolved with rho squared times rho, this last term. And it comes with a minus sign. So this one's going to go in the negative term. So what's very difficult is to regroup the terms, but it's going to go in, in this negative term, this big negative term. Okay, so I think I want to finish here this part about discussion of mean field limits. And I want to use the time that's remaining to show you a little bit how the technical tools, I mean, the quantities, the ideas that I've described so far that have been introduced for these mean field limits are also useful for doing statistical mechanics of these Coulomb and Riesz systems. So when you really look at the Gibbs measure, which is the invariant measure associated to these dynamics. So if that's okay with you, I will switch to that topic now. But it's a good time to, if you have questions to ask about the preceding part, it's a good time to take questions. No? Why do you have any questions?
Okay. In your case, we just do for the sub Coulomb K, right? G is the sub Coulomb K, right? And how about Coulomb K and super Coulomb?
You mean which method?
Yeah, for your methods with max.
So for the method with max, it doesn't work in the Coulomb and super Coulomb, because it's what I said here. When you differentiate just the modulated energy, the expectation of the modulated energy in time, you get a term that doesn't have the right sign, and you don't know how to get rid of it. So the only way to get rid of it is somehow to add the relative entropy.
Okay.
So in the computation here, adding the relative entropy is what allows you to cancel out the term that's problematic. And so what I didn't say is when you regroup these terms, of course, it's implicit. It's very important that you have this beta in front of the modulated energy, because the cancellations happen exactly precisely.
Okay.
So I don't know of any other way. And it's also natural, right? Because every time you have noise, somehow physically it corresponds to an entropy. If you think in terms of free energy, the temperature really brings you naturally this entropy. You want to have it, right? So when beta is infinite, you formally you would want to put 1 over beta here. You cancel this term. You don't need the entropy. But when there is beta, it's natural to see the entropy. And actually, I'm going to show that also in the statistical mechanics context, which I'm going to describe now. Okay. Okay, so now I want to describe a little bit statistical mechanics of Coulomb-Riesz systems and gases. In physics, it's called gases. Okay, so I mentioned this in the introduction. What we're interested in then is, you want to consider again these energies. So I write them Hn with straight H, so it's not the same as the relative entropy. Try not to confuse, right? So straight H here. And let's put here 1/2, so I don't count the interactions twice. Have G of Xi minus Xj, so these Coulomb interactions. And you can add, it's preferable to add a confinement potential, because otherwise if you work in the whole space, the integrals don't converge. Okay, so V confinement, it has to grow. It has to grow fast enough. And G is what I described, Coulomb or reason. So let's do just super Coulombic. So between D minus 2 and D. And what you want to consider now is the Gibbs measure. 1 over Z depends on n and beta, e to the minus beta hn. But in fact, what I'm going to do here is I'm going to put n to the 2 over d minus 1 times hn. That's just a more convenient scaling of the energy with respect to temperature. So it turns out that this is the right scale in some sense. But if you let beta depend on n, then that doesn't matter whether you put a factor here or not. You could just change beta into this quantity. But okay, this is good. And in particular, if you're in dimension 2, logarithmic case, this doesn't matter. So in fact, what I would like to say, it's not 2 over d, it's s over d. Okay, so minus 1. It's s over d. So in the Coulomb case, of course, it's 2 over d minus. No, it's minus s over d. Yes, it's minus s. Okay, so this is the distribution on particle configurations, which is such that, for example, if you take this as initial data, it doesn't evolve in the sense of the mean field limit, right? So it's the stationary state. Pn is a stationary state for the Liouville equation that we've discussed before. Okay, so in statistical mechanics, these things are very much studied, in particular for random matrix theory. When G is minus log and G is dimension 1 or 2. The Coulomb gas in higher dimensions, only recent that it got a sort of revival, because there was a big statistical mechanics literature from the 70s. 70s statistical mechanics with works by Jean Covici, Lieb, Lebowitz, Martin, and Leonard. Okay, there's a sort of large literature and then recent revival. And of course, what we want to understand here is what happens as n goes to infinity. So distribution of points. As n goes to infinity, the macroscopic distribution, so this is the mean field if you want, plus the microscopic arrangement. Okay, so the first thing which I mentioned in the first lecture is that this is related to a continuum description in terms of densities, which is that you should look at these functionals E of mu, where you put back the diagonal. No? And you should look at the minimizer of this. And you expect that, so the minimizer is called the equilibrium measure. It's unique. And it's expected that, but the law of large numbers, it's not only expected, it's proved. It's that if you look at the empirical measure of the particles, they converge to, so let's call it mu v now, it's slightly different notation from before, but it converges to this, okay, except with very small probability. It's not the case for every configuration. But so one of the things you want to know is to quantify what is the small probability and what are the deviations from this. So what is the behavior of the fluctuations, for instance? This is the law of large numbers. Right, so what is this, the distribution of this? Is there a limiting behavior? Right? And what is the scale at which the approximation is correct? Okay, so it turns out that well, this is an energy, right? This is the sort of continuum description of the energy. And I told you before that when you have temperature, this is the remark I was making at the very end. When you have temperature, you should add some entropy. So in fact, a more correct continuum description E beta of mu. So it's 1/2 d mu of y plus v d mu. But now you add some integral of mu log mu, so some entropy term, with an inverse temperature theta, which is the effective temperature you should take is beta to the, so 2/d in the Coulomb case. So let me think. It's 1 minus S/T. I think. Okay, so, oh, sorry, it's an N. This times beta. So what happens is that, well, because S is strictly less than D, this 1 minus S/D. Okay, so this is the opposite, should be -1 plus S/D. This thing goes to 0. No, it goes to plus if I have it wrong. Exactly. So it's +1. So this goes to +infinity. Okay, so there's 1/θ in the regime that I'm looking at. This is a very small term. This is a very small correction. If you fix beta, right, you let n go to infinity, this is like a small correction. So the minimizer of this should be very small to the, very close to the equilibrium measure. So it's really a small perturbation of the description. However, it is more accurate and more correct and more convenient, in fact. So why not use it right away? So instead of the equilibrium measure, I advocate using what I call the thermal equilibrium measure, because I couldn't find a term in the literature. And of course, it appears around. It's not. And it solves the PDE because it minimizes this this energy. So if you write what it solves that G. So I have the equation somewhere. So let's call it mu theta. It solves that G convolved with mu theta plus V plus 1 over theta log mu theta is a constant phenoid. So it's always a positive density. It's always regular. And it always has full support. So what happens typically is that the equilibrium measure I mentioned to you, it tends to be things that have compact support. The density of the equilibrium measure, something like that, right? You have the support of the equilibrium measure, and then suddenly you have a certain density, which is regular, and then you're back to zero. But the thermal equilibrium measure is going to look more like this. So it's going to have exponential tails. I'm going to do the same. Imagine a picture where you do kind of the same. And then you, again, exponentially converge back to zero. So mu theta, it has tails like e to the minus v. So it depends on your confining potential, right? But so if your confining potential is quadratic, for instance, then the tails are going to be Gaussian. So it's no longer compactly supported. Okay. And so now what I want to do is I want to show you the splitting formula that allows to recover, to see the modulated energy appear. So we're going to rewrite the energy itself. And I'm going to rewrite it in a continuum version, some sort of an integral version, rather. But I have to remove the diagonal, of course, and I write here the sum of delta xi, sum of delta xj of y, right, plus n integral of v, sum of delta xi. So far I've done nothing, just rewrite the energy, which you remember is the sum of g of xi minus xj plus n sum of v of xi. So I can rewrite it like this. And what we're going to do now is to insert mu theta. So insert mu theta. So you do as if sum of delta xi was roughly n times mu theta, plus you add a correction. So this is equal to what? So this is equal to 1/2 integral gx minus y. This is going to be an n squared. D mu theta of x, d mu theta of y, plus n times integral of v d mu theta. So that's if everything was mu theta, plus I add the error term. So I'm going to have a 2 times a symmetric term, right? Where I have a mu theta still integrated with the difference. Something like that. And because mu theta is regular, I can, I don't have to worry about the diagonal anymore when I integrate with respect to a good regular density. But then what I pick up is I have my third term, which is, so I have this also, I have integral of v sum of delta xi minus n mu theta. And the third term is 1/2 integral g of x minus y, sum of delta xi minus n mu theta squared. And here you recognize the modulated energy, right? So this is 1/2 of n squared times the modulated energy of xn relative to mu theta. So that's my sort of quadratic term. And then I just have to worry about the middle term. Okay, so I have this middle term. Middle term, which you can regroup, and you're going to use the equation from mu theta, obviously, because mu theta is a minimizer of something. So when you expand around mu theta, something nice should happen. It's not coincidence. And you can recognize here in this middle term, here I can recognize a convolution of g with mu theta. So I have g convolved with mu theta. And here I have an NV. So I have g plus v, and I was missing an n here. So I have an n, g convolved with mu theta plus v multiplied by the sum of delta xi minus n mu theta. And what is g convolved with mu theta plus v? Well, there's an equation for mu theta, you see it here. So g convolved with mu theta plus v has a precise expression. It's a constant. This is constant minus 1 over theta log mu theta. And so the constant that integrates to 0 because here I have exactly n term. And here this is a minimizer. Of course, when I said minimizer, I also always mean among probability measure. So minimize among probability densities. And here, again, this is a probability measure. So this C doesn't really appear in the end. I just have to compute minus 1 over theta, the sum of log mu theta of xi, minus n squared integral of mu theta log mu theta. Okay, so if I put everything together, you see this computation, the first term here, that's a piece of the energy, that's the energy of mu theta. And here I have the entropy, I have 1 over theta. Okay, so if I put everything together, I get that Hn of xn is equal to E theta of mu theta. That's the leading term, the term that doesn't depend on the point configuration. So I have an n squared. This is because I collect the entropy here and the piece of the energy there. I have, for my middle term, I only get this term now. This one is theta sum log mu theta of xi. And I get the modulated energy with an n squared. So what I'm saying here is that up to some term here, which looks like some sort of effective potential. So this is like an effective potential energy. Here I have a constant. I don't really have to worry about it. So my energy up to a constant and some effective potential energy is like the modulated energy. So I'm going to plug that back into the Gibbs measure. Okay, so this is the proposition. That's the splitting formula. It's just a pure computation, not so surprising once you think of it. But, okay, so plug into dPn beta, and you get that the Gibbs measure you're trying to study can be rewritten as 1 over z and beta e to the minus. So now I have my my factor that I have to pay attention to. So beta, what did I say? And to the 25. n to the minus s over d. So I have a 2 here, so it's 2 minus s over d, e theta of mu theta. Then I have some exponential minus beta and minus s over d over theta, sum of log of mu theta. Okay, but so this is where I chose theta in a way that was not random. Theta was chosen to be n to the 1 minus s over d times beta. So n to the minus 1 over d times beta. This is supposed to be. So it's going to supposed to make exactly 1. Maybe I forgot something. I have an n here, I think. That, okay, I'm missing an n, that's all. So here there's an n. Here there's an n, and so here I have a 1 minus s over d. And you see this factor here just becomes 1. This is 1 by choice of theta, by definition of theta. And then I'm left with the exponential minus beta n minus s over d, so 2 minus s over d f x n theta. Okay, so now everything that's constant, I can put it back into the partition function. So all of that, I don't really have to worry about this. So I can write as 1 over z n beta, let's say prime, after I've simplified all my factors, possible constants. I can write e to the minus beta over 2, some factor, depending on n, type f, x n mu theta. And the exponentials of the logs of mu theta, which by the way come with a plus sign, because here I have a minus. That makes, okay, exponential over log, it's just a product. So it's actually d mu theta of x1, d mu theta of xn. D mu theta of xn. Okay, so this is what comes from this effective potential. Because it's a log, when you put in the exponential, it comes out. It comes out here, and that's very convenient. Instead of sampling with respect to the Lebesgue measure, you sample with respect to the mu theta measure, which is completely natural. And now you have to understand the Gibbs measure associated to the modulated energy. Okay, so this evening, I will show you how from this, starting from this formula, you can very quickly obtain some concentration estimates. So we're going to obtain concentration estimates around the thermal equilibrium measure. And give you a flavor of the techniques to prove a CLT, so a central limit theorem for fluctuations, which is going to end up using the commutator estimate again. So this is the menu for the last lecture, which is tonight. Okay, time for questions if there are any.